All right. So first thing to understand is that we understand the core structure of Sandy Bridge. And the core structure, here's a couple of legal disclaimers, probably saying that nothing we say here is true or might change on short notice, something like that. And even that we might optimize kind of workloads for our own architecture. This is what we are essentially interested in. And this is a pretty complicated high-level diagram of the Sandy Bridge core. It is, well, any of these blocks in here have a quite complicated functionality usually. And between the blocks, there's even more units, which we don't show here. Buffers, fill buffers, load buffers, you never know, which might become important at one point. But this is essential parts that we think are most crucial for performance optimization. This is mostly too complicated. I assume that most people here are not from processor design, and they don't care so much about this kind of diagrams, and maybe ideally we would use a compiler, switch to O3, and just get good performance. It doesn't work that way usually, right? So we have to understand a little bit about that, but this is too complicated. We need to associate a couple of parts of this with particular functionality that comes from general considerations of computer architecture and design. There's a couple of technologies that Sandy Bridge implements, or mostly all processors nowadays do that. One of the most prominent one is certainly pipelining, and we will see that this is one of the features that brings us most performance, but it's also, it has the property that it's also disturbed the easiest. So a pipeline can be disturbed pretty quickly by some things you do in the code, just by doing something wrong. By the way, of course, you will get all the slides, so you don't have to write this stuff up. Right? So another technique that very much adds to the performance is branch predictions, something called out-of-order execution, which already gets a little bit esoteric, superscalarity, and SIMD execution. All of these techniques interplay a little bit with one another, and actually add to performance, but can also handicap performance in some way. And we need to understand how and why. Usually, the first general steps every processor does is it fetches a new instruction. This is what it starts up with. I mean, if it comes up, it will bootstrap and just get a new instruction, load the operating system probably, right? And the first thing after that it will do is decode this instruction. It will find out what it wants to do with it. Is it an arithmetic instruction? Is it a memory operation? Is it something else, right? And if it has found out about that, it will try to execute this instruction. If it is something that is more arithmetic, like an addition, it will divert it to the so-called ALU, the arithmetic logic unit, and we'll see we have a couple of those in our processor. Or if it is something more organizational, probably a memory access, it will divert it to the unit that performs a memory address and loads this into the local registers. And if it has some results from these operations, it will write back the results into something called a register. And a register is just like something like a local storage. We have pretty few of those visible to the user. Internally, we have a lot. And we will just see what registers probably means. Okay, so we just saw there's fetch instructions, decode, execution, memory access, and write back of the results into memory. And usually people view that as one thing. We can execute that in a single step, right? We will just execute a single step and wait until it's finished and then fetch a new instruction. What is a little bit more enlightening in this case is if you split it up into different execution units, and then, so these execution units are called stages of the pipeline, and then consider the outcome result. But if you now look at that, we can actually peruse the individual stages while, for example, the first instruction was fetched. We can already, and the first instruction is decoded, we can already fetch the next instruction. While the first instruction is executed and the second instruction is decoded, we can already fetch the third instruction, and so on and so on. So the first thing that actually adds to the performance, and people came up first with it very early in the development of computers, was to actually split up the execution into pipelining. Usually what brings that in terms of performance? What the original performance was the number of the time it takes to execute an instruction as a total thing, and times the number of instructions, the total time of the execution. And in the case of pipelining, we can ideally, over a longer workload, we can divide this by the number of stages. So we get immediately factors out of this performance tuning in the chip. Now this seems to be pretty good, and people like this idea. They actually pretty early in the development came up with this idea and executed it successfully. And greatly nowadays adds to the performance of our processes, of course. We'll see in the following that there is a couple of facts that interact in the pipeline that handicap this performance. And we carefully need to take care of this, that this doesn't happen, because everything or all the performance depends on in current process is keeping the pipeline busy. If you stall the pipeline, where the performance comes down pretty quickly. So all analysis and optimization methods hereafter are basically set up to keep the pipeline flowing. So what can stall the pipeline? So we had all these couple of steps, like we fetch an instruction, we decode it, we execute it, we have memory access, for example, or we write it back. So, for example, if we want to fetch an instruction, we need to know which instruction we want to fetch. Consider a situation where we have an if condition and say, if a given variable is greater than 1, we want to go this path, otherwise we go the other path. So in this case, we don't know what the next instruction is because it depends on the outcome of the comparison. So we probably cannot even fetch this instruction because we don't know what the next instruction is. We may not be able to decode the instruction because there was no instruction fetched. Right. We may not be able to execute the instruction because the data that the instruction acts on. So for example, usually instructions come in kind of a function form, saying function name and then a function argument, maybe several arguments. Because some of the arguments might not be available because they depend on an earlier step of the calculation. So we have to wait for the actual execution of the previous instructions. We might have a memory access that cannot fetch any data because there is no data available, for example, in cache. There is no data available in the second level cache. I might have to go to the main memory to get the data. I might have to go to the disk to get the data. So we might have to wait before something happens. Right? Or I can't load the data into the register that was given to me, into the very local memory, because this register might still be in use. So all these kind of things can happen, and many more can happen. I mean, there's an infinite amount of problems in the pipeline can happen. And all this limits the pipeline execution. And this is to be avoided. The first thing we want to consider to improve the situation is actually predicting branches. Because when we look back at the previous slide, we had the issue that we want to fetch an instruction, but there is essentially, we don't know what instruction we want to fetch because might be a condition that actually tells us which the next instruction is. So the way out of that is the branch prediction. So we try to actually speculatively say which instruction is the next based on some considerations we have from earlier execution, for example. So we might remember what the last if condition was. Say we're running in an if condition. If s equals 1, then do this. Else do something different. And we know that this condition always fails. It's maybe something like we ask for an error. So if you have an error, then do something. Otherwise, just keep on going. And we know that this never fails. Just in case of an error, it might fail. So we just might be fairly sure that we can skip this step and just jump to the next usable information which doesn't treat the error. So what we do is just we speculatively prefetch this, and we prefetch that on this, based on this algorithm. This is a very simple one. It doesn't necessarily mean we use the same one in the Sandy Bridge architecture, but it is representative. Essentially, what branch prediction does, it creates a table which has all the addresses of the jumps. A jump is a comparison, for example. So it compares two values and just gives you the results, and all of these comparisons are tracked in the architecture via their address. And there's another field that consists of 2 bits, and these 2 bits vary depending on which branches are taken. So for example, we might have a default behavior. We say we never predict the jump here. We never predict that there is a branch taken. We never predict that the if is true. So in this case, our start condition is 1, 0. So we run into this case, for example, and our branch prediction will just execute happily on because it will not take the branch. Right? And in this case, if you the second time haven't taken it, and it turns out to be true, we will end up in this stage. We will decrease the number by 1. So there's no jump predicted. And while we don't predict this jump, we will always stay in this state. Just a very simple state machine. However, if we predict it once wrong, we might go back to this state. So we increase it by 1 if we predicted 1. And if we predict it wrong a second time, we might jump to this space, to this state, 1, 1. And then while we take the branch, we might stay in this state. So we have a bistable system that has two attraction points here that allows us to affect, and this is already a pretty effective way of doing it. Of course, there are more advanced techniques in the Sandy Bridge processor, but this is how you can envision it. All right. So what happens if we predict it wrongly? Because we always had the chance that we just, for example, in the very beginning, we just have a 50% chance of hitting the right results, and there's just a default behavior being expressed as a single integer. So what if we predict wrong? In this case, everything that happened before this wrongly taken branch will have to be cleaned out. We clean out the whole CPU, meaning we clean out the whole pipeline. Everything will be set to a default value, and we start execution back at the point or the address where this branch was taken. So we never can go in the execution beyond this point where we haven't committed the result of such a branch. We have to wait for the branch, otherwise we have to clean out everything. So in order to be causal, we never can go any further in the execution. This clean out of the whole process is called a pipeline flush, and it's one of the most evil things that can happen. It became a lot better with the recent generation of processors. However, it is still something that costs you in the order of the pipeline instructions, or time cycles, clock cycles. So if you have a pipeline flush, our pipeline is roughly 14 to 15 stages, or at least we can envision it in this way. I mean, there are probably even more of that. Then you will spend 14 cycles just on reestablishing the pipeline results up to that point. Sure.
Can you go wrong again if you're what is known?
Well, I can immediately wrong. I mean, consider something like a Monte Carlo, where I just draw random numbers and say between 0 and 1, and say if it's larger than 0.5. You go, well, statistically wrong every second. So a Monte Carlo is something that is, for the pipeline, is absolutely evil. Right? And it might, I'm not sure if there is a technology actually tracking that and seeing that this point is actually not predictable and it will stop predicting it. It will just wait because it flashes out every second cycle. It might still be more efficient to just flush the pipeline instead of waiting for the execution. So in earlier processes, we had pipelines that went up to, I think, 30 stages, and you had to wait very, very long before you actually could go on computing again. Nowadays, it's not so big an issue anymore. So Monte Carlo is a disaster for a pipeline. So in this case, all these kind of, it's the traditional way of how people actually catch errors in Fortran is like give back a status and then ask if the status has been 0. This usually poses a problem on the first execution, but on all succeeding executions will not be a problem anymore because the processor remembers which branch was taken. Right. Good. So the next issue we had, where we could now, in principle, very effectively predict where we're going. So we don't have the issue in the fetch and the decode anymore, we assume. But we still have an issue if we want to push the next instruction into the execution stage. But the execution stage might still be busy. There might be instructions that take longer than others. Say a multiplication takes longer than an addition. An exponentiation takes longer than a multiplication. Right? And there might be even, or logarithm, right? They're usually very long-running, long-latency instructions. So we might not be able to push the next instruction into the execution because it is still busy. But the instruction that would be next may be just something that doesn't affect the execution at all. It might be something that is just a memory access. So it's uncritical. We could just let it pass by. And this let it pass by we call the out-of-order execution. It's actually a pretty complicated thing, and it's something that, if you look at it from an algorithmic perspective, can be very delicate. It's something built on something that is called the Tomasulo algorithm. Came up in the early, I can't remember, 70th by IBM. It's a very clever thing. It's an unbelievably clever thing what they did for increasing the performance, and ever since was something that drove up the performance of processors. We don't have it in one of our very recent architectures, which is called Mike. And if you try to program on an in-order processor, you will see how difficult this is. To live with the fact that you can't bypass an execution that blocks a certain execution unit. You really have to think about in which order these are put into the assembly. Okay, so what do we do to actually make out-of-order execution work? So we have this blocked, speculatively blocked execution unit here, and we want to have a memory access bypassing that. So what we need is an additional pipeline stage called the dispatch. And the dispatcher is actually looking at the instruction and see if there is dependencies between them. These dependencies might be either in the form of, is it an arithmetic or is it a memory instruction? It might be even different arithmetic instruction. Is it an integer or floating point instruction? Could I pass it into different execution units? However, it might be something completely different. Does it require resources that they both of the instructions that succeed each other share? Do they actually use the same registers? Do I have to do something? Right? Is there dependency between the instructions? Dependency is usually a critical point. Okay, so we introduced this new stage called the dispatcher that looks into this. We treat it as a black box. Every processor nowadays has it. Every processor has out-of-order execution. And then we might have all the execution here in the middle, and possibly an independent instruction could bypass a blocking instruction. Right? However, in the end of the whole execution, we must reinstall the causal order of the instruction. We must reinstall the original order of the instructions. Otherwise, we'll get fancy results. And this is done by even another additional pipeline stage called the retire. The retire takes care that everything that is written back into the state of the machine, write back basically creates a state of the machine. Oh, I'm good. Oh, here's a pointer, really. Let me see. That's really good, thank you.
Yeah, it works.
Is it?
Yeah.
No?
Should work. If it's out of battery, just let me.
Oh, it's off.
Yeah.
Okay. Yes, good. Oh, thank you. That's very helpful, actually. So the write back creates maintains the original order of the instruction. It needs to be written back into the state of the machine in the original order, and the retire just takes care of that. It remembers in which way the dispatcher dispatched the instructions, meaning there's a table which tracks that. This has a certain length, by the way, this table, and we will see on the Sandy Bridge block diagram which length this table has. Retire just takes, well, in principle you could combine it, right? But retire just takes track of the order, which order the instructions came in. The write back actually executes it. But this is just because we had this stage before, you could skip it. Right? We usually deal it as a separate stage. Okay, now we have a dispatcher. So we have this little fancy unit that could all take care of the dependency of instruction. So what actually keeps us from aligning the execution units in a parallel manner? You can basically just have a lot more execution units because the dispatcher takes care which dependency exists between the individual instructions. So it will thoroughly just pipeline it through these different execution units, and the retirement stage will take care that everything is reordered again after the execution. And the write back will then commit the results to the machine state. So this is something we call the superscalar architecture. This is ordering different execution units in parallel to each other. And this is you see immediately that you potentially gain factors in performance by doing that, just by adding execution units. Right? If you have a lot of floating point execution, you could potentially add like many of those and achieve always n+1 performance. Or if you double them, you get twice the performance out of that. Right, sure.
Do you need out of order in order to have a superscalar?
In principle, not, no. You don't have to have it. You don't need to be out of order to have superscalar. For example, Mike is essentially superscalar, but it's in order. But it has a very delicate scheme of dispatching this stuff. But it is more insightful in this way, I think. I mean, you don't have to have it. It's not conditional. Okay. So the last thing is the last generally used technique that we want to consider in our block diagram is simply execution. We saw that we had all this big number of execution units we could probably put into the CPU. However, we might need to deal with even more data, even more floating point instruction that we actually have to execute. And in order to improve the situation, I mean, do more additions, do more multiplication, more exponents, whatever, we can just introduce an element-wise computation of a vector. It's not a real vector. It's just a bit of memory, of local memory, that's called a register, that holds a number of different elements, for example, of an array, including its values. And we can add them all one by one. This execution is pretty efficient because we know all of them are additions. We can implement it in a very efficient manner. We don't have to actually respect dependencies between them. And this is something where most of the floating point performance comes from nowadays. These vectors have grown from 64-bit to 128-bit for a very long time. Now, just with Sandy Bridge, have grown to 256 bits. And the doubling of the performance on Sandy Bridge, basically, or peak performance on Sandy Bridge, basically is found in this, in the fact that we doubled the vector width. We nowadays can treat 4 double precision values at the same time. All right. This is what I just spoke about. And now let's look back at the Sandy Bridge. This is the same diagram again. Now, the question is, can we identify what we just talked about? What is the individual part? I mean, we see something up here. Here's pre-decode. Here's decode. Something there must be the instruction fetch, right? So there's an instruction fetch. There's even an instruction pointer. You can print it out if you like. It just tracks which instruction you're executing. And here is a decoder. So here the instructions come in here. They come from the level 1 instruction cache. So they go in here. There's something called a micro-ops cache. We'll speak about that later. And they go into something allocate, rename, and retire. In this case, the retirement unit has been put here. Because when we allocate and rename, meaning we are assigning registers to the execution. I told you that officially to the outside, there's a number of local storage areas called registers. There are only 16 of them that you can use to store, say, a single 64-bit integer directly on the chip, directly very close, one cycle distance from the execution. However, internally, we have a lot more of those. And if one of them is busy, so if we can't dispatch it into the execution because it depends on another register, which is a dummy dependency, then we rename the register into something else. So we don't depend, actually. We can detect if there's dummy dependencies in the algorithms. So there's one big bit here, and this big bit is a dispatcher. The dispatcher we call a scheduler. The scheduler takes care which instructions come in from the allocate, rename, and retire, and of which kind they are. They might be something that is floating point. They go here. There might be something, there's integer. Where do we have integer? Oh, we don't have integer in AVX. Okay, it's not especially mentioned here. Because AVX is currently, in the current version, pretty much integer-based. It might be a memory instruction, so it goes to one of the ports here, and we'll just look if which port is busy, because there are two parallel load and store ports. And after the execution, we'll go back essentially to the retire. The retire, in earlier diagrams, we had that a little bit more cleverly arranged, but the retire basically is still connected here and will take care that everything is reordered. All this bit down here is out of order. Everything below the dashed line is out of order. Everything above the dashed line is in order. So the front end and the back end, the retire, is in order. Everything else is out of order. Now, what are the special features compared to earlier architectures is that we now got 256-bit SIMD units, right? That allow us to simultaneously compute 4 double adds, 4 double adds, 4 double multiplies, and 1 shuffle each cycle. And we will see what a shuffle is later on. It's a data rearrangement in the vector. In contrast to earlier architectures, we have now 2 symmetric load and store ports. When we double the vector width, so we double the floating point performance, we must also take care that there is enough memory bandwidth that actually allows us to satisfy this this floating point performance. So it doesn't make sense to make this a lot bigger without taking care of that. So we also doubled this. Essentially, we can now load twice as fast. It has some, drawbacks, which say this is not absolutely true, but the memory performance on Sandy Bridge is much better than has been on earlier generations. And they have been very good already. We currently get around something 100 gigabyte per second, I think, in top, out of a dual socket system. There is something called a 1.5K micro-ops cache. So everything that lives in the out-of-order section here is not really executing what you told it to. You'll find if you do a command called object dump on the command line of your binary, you find you have assembly instructions, machine instructions. You can also look at it in a hex editor, and you see that that's all basically commands like move something from one place to another, add something to a given place. And internally, this is not what we execute. We translate this via the decoders into something that is called a micro-instruction. And a micro-instruction is something that is a little bit more adapted to the underlying hardware. So internally, we execute different commands. Usually, one assembly command translates into one micro-operation. It doesn't mean there's a big difference, but there might be a big difference. For example, do we combine different successive instructions into one, or we might split up one instruction into two micro-operations. We can do that. And we do that in a way that is most efficient. And this micro-operations cache, it will basically store decoded micro-instructions, so we don't have to use a decoder. This is actually not a feature that is made up for performance only. This is mostly a feature that is made up for power efficiency, because we can shut off all the stuff before. We can just close it down while we serve our instructions from the micro-operations. Good, let's quickly check the time. Good. This is something, so going back to this diagram, this was a core. This is a single core of a Sandy Bridge processor. The Sandy Bridge processor has 8 of them. And they are arranged in kind of slices. You always see these 2 cores and one L3 cache are combined into one slice through this die. This is a full processor. And each core and each level 3 cache, they always belong together, are connected with the other ones by a ring system. It's actually a bidirectional ring, so it goes this direction and that direction. And I have some more data on later slide what the actual performance performance data on the ring is. So you could imagine that if you have something sitting in the cache here and being needed in the core here, it has to go through the ring and through a number of hops. So internally, this system is a little bit NUMA-like, right? But you will never feel it. It's very efficient. It's very nicely made. In the early stages of the processor, we really had the feeling that you could measure that out, because if you went through grids with different strides, for example, you could see you were always hitting different latencies in different caches, and you could actually see that it was further away and took longer than others. So, but then they hit that via the algorithm that actually assigns the data to the caches. Right, so what else do we have on the chip? We have the cores. We have level 1 and level 2 caches here directly attached to the core. We have a big level 3 cache. We have the ring system. There's a QPI. The QPI, the quick path interface, that connects 2 processors. So usually on HPC systems, we have a 2-socket configuration. So there's 2 processors in one box, and both of them are connected via a point-to-point protocol called QPI, and there are 2 links of that connecting that together. Additionally, each of the processors has an onboard PCIe controller, so it can control a PCIe device. Of course, Sandy Bridge is an architecture that has an integrated memory controller. Internally, a 2-socket system is a NUMA setup, a non-uniform memory architecture, meaning that every chip in the 2-socket configuration has its own memory controller, and it has to communicate to the other processor, which share the same address space, if it wants to get data from there, and it might end up with a performance penalty. Usually, the access time to the local memory is twice as fast as to the remote one. That's a good rule, in general. The memory controller has 4 channels, and Sandy Bridge can consume DDR3 memories up to 1600, DDR3 1600. This is internal ring details. So the ring
has a width of 32 bytes each direction. The frequency is actually variable. It varies with the CPU core frequencies. And the bandwidth at 3 gigahertz core frequency is roughly 100 gigabytes, 96 gigabytes. It can transfer data from one point to the other. It takes one processor clock per hop. So if you go over different caches, basically slices, to deliver a cache piece of data to another core, you will consume a single processor cycle per hop. So it costs you, for example, in the worst case, 4 cycles to access a piece of data, to deliver it at least. Right, and this is the total configuration of the platform. This is not identical to what Cray has. It's very different. But this is the general setup we deliver. This is essentially what I already explained. There is 2 Sandy Bridge CPUs in the package. It's similar to what you'll find on the Cascade. There is QPI links between the processors, 2 of them, running at 8 gigatransfers per second. The processors have, in the most powerful stage, 4 memory channels, being able to consume DDR3 1600. What else do we have? I think that's basically most of the important stuff. There are always smaller configurations that are possible. All right. Good. Okay. So the last thing I want to speak about is AVX, because we will need it later on in the compiler labs, because everything from now on will actually aim at making floating point performance via the vectorization. So let's spend some time with AVX, the last minutes. Key features of AVX is, of course, its wider vectors. We double the floating point performance by just making the execution of the vector twice as wide, allowing us to treat twice many floating points values. There is enhanced data rearrangement instructions. Essentially, we will learn about this in the hands-on for the Intrinsics, how to do really data rearrangement and what it means. Because it doesn't help you a lot if you have element-wise processing of various super complicated functions like exponential or sinus or whatever. If you can do it one per element, you need to rearrange the elements in this vector in a way that they really make sense. For example, that they represent a differential equation. Otherwise, it will be pointless to make something like that. Whoever has programmed assembly in Intel IA assembly knows that usually in the standard 32-bit assembly there is 2 operands to each assembly instruction. So we can say, for example, move register 1 memory address X, and it will go to the memory, get the address X, and move it into the register 1. In AVX now we have 3 and 4 operands. Why is that important? Because if you do, for example, an arithmetic calculation saying add register 1 and register 2, then we will override one of the values, obviously, because we only have 2 arguments. Now, with 3 operands, we can save we can maintain the value in the 2 source operands and write the result to another register, which will actually save us a save command to another register. So the code will be much more compact with AVX. And there's also very flexible unaligned memory access support for AVX, and extensible new opcode means we can do a lot more AVX commands in this subspace of the instruction set. Okay, so this is the basic functionality. Of course, everything that is element-wise will be present. So we have additions, multiplications, square roots, exponents, divisions. That's all present, right? Everything is executed element-wise. So element by element, we can do an addition. Fine. Pretty unexciting in principle, because you couldn't you couldn't do a lot of different things with it. Now, what you need to create an efficient assembly vectorized algorithm is permutes and shuffles. Permutes, what they do is actually they allow you to rearrange the data in the vector. Right? So you can essentially reflect the structure of a particular field or a particular, like, say, differential operand in a discrete manner in this vectorization structure. Okay, so you see there's a little dotted line in here between. So this is a single precision vector. It can AVX can treat 8 single precision values at the same time, and there is a little dotted line here between. And this dotted line means you won't be able to permute over this line. You only can permute 4 of them. Why is that? Because our previous instruction that was only 128 bits, and we basically doubled the whole instruction set. Right? So this lane is kind of a legacy thing, and we can't permute over this lane. In order to exchange data between the 2 lanes, we have to exchange the lanes. And this is done via 128-bit permutes. So we can exchange whole lanes between the vectors. Okay. There is the possibility to, oh, the font really screwed up a little bit here, to do insertions and extractions into a 256-bit vector. For example, loading 128 bits in the upper part or from the upper part into the lower part and so on. What's also usually often necessary is broadcasts. You can distribute single values from the memory or from a register into the whole vector. This usually expresses constants in a grid computation, for example. And this is very often used. Right? What is a very nice feature and often very extensively used by the compiler is conditional SIMD loads and stores. So we can mask out part of the operation. Most operations in AVX can be masked. So there is a register given that contains a mask, and this mask tells, load this, but don't load that because it goes over the page boundary, for example. It will cause a segfault. And if you do that, you will have no segfault. You can go load with a vector over the boundaries of your allocated memory, because if it's masked out, it will not cause a segfault. It's a very nice technique if you try to vectorize very extremely. Right, so a complete masking architecture. Essentially, I just spoke about that. Yeah, 3 to 4 operand instruction format. This is actually the nicest thing about it, I think, apart from the fact that it's 256 bits. Do we have here? Exactly. So here is an example that is written in a syntax that accepts 2 arguments. So move APS, so move the content of register 9 into register 10, and then add the register 1 to the register 10. This will override the register 10. So we have the operation here before just the add is actually made to save the content of the register 10 because we might need it in a succeeding computation. Now in AVX, this comes down to being a single instruction because we can write the results in the register 10 from the sources register 9 and register 10. So we have a lot less rearrangement before we actually execute something. We don't have to save. We don't have to arrange memory operands in a way that they actually fit the arithmetic instruction and so on. There's also a format that accepts 4 memory operands if it basically there is a control integer here that or a control a control mask or whatever you want to call it, where it executes an additional blend instruction. Blend means we can copy two vectors together, and this blend instruction basically has a control mask that says, I'll take this value from the first vector, and if it's 1, I'll take this value from the second vector. And there, essentially, we need a 4-vector format. Okay. What?
This apparatus is pretty common. This on the right-hand side, it doesn't actually execute 2 commands, so it's just
This one?
on the right-hand side, when you do add PD with
Yeah.
3 inputs, when you have
Yeah.
3 inputs, does it actually execute 2 commands, or it just does this directly?
No, it does that directly.
Okay, so
It does that directly.
and it's faster.
Yeah,
Or-
it is.
or-
It depends. I think, of course it is faster, essentially. But what it also does, I mean, it keeps the instruction cache very compact. You don't have to load that many instructions. It makes the code a lot more compact. And the most efficient way of getting better performance is actually to execute less code. As long as we can execute this as fast as that, everything will be fine. We save instructions. And the decoding and everything will be much quicker. So, yes, we replace it by a single instruction, and we also execute it in the same time. So essentially, it will be faster in execution, and it will be faster in decoding, and it will be faster in, well, more efficient in storing, because we don't have to store so many instructions. Essentially, all of these instructions take a single cycle, and this takes a single cycle. So it will be twice as fast, which is pretty cool, actually. Okay, so we're almost there. Good. Okay, this was essentially the processor technology crash course. This is about the basic blocks of Sandy Bridge. And just mind you, it is the basic blocks of a general processor. It can also be another processor, as long as it's, for example, in order. So the design principles of Sandy Bridge are not from another world. They're just efficient. But they orient themselves in the standard state-of-the-art way of how people design computers. The central element of the whole CPU is the pipeline. It's essential to keep the pipeline busy to get good performance. When we stop the pipeline by either breaking the execution flow, by breaking the branch prediction, by say, making out-of-order execution less efficient, and there are ways to do that, we will get worse performance. So keeping the pipeline busy is something that is what people try to do when they optimize for performance. Important concepts is superscalar pipelines. So we can execute different instructions via a dispatcher at the same time into different execution units. Be aware of that when you write your code. So mix them, for example, is always a good thing. And the compiler usually takes care of that. The out-of-order execution, if there is dependencies between different instructions, it will cause the out-of-order execution to develop dependency chains. And if you remember back the diagram of the pipeline, you see there are 56 instructions that can be stored in the scheduler, and then it will overflow. It will stop the rest of the pipeline. If you have a dependency chain that is longer than 56, we'll stop. So long dependency chains between instructions will cause the out-of-order to break at some point. SIMD, so vectorization is certainly the single point for floating point performance currently. There is not much more to come. So we know that the frequency goes into the power consumption by square. So basically, it doesn't make sense for us to grow the frequency a lot because you won't allow us, well, you wouldn't want to pay the power bill because we'll go quadratically with the frequency up in the power. On the other hand, the power consumption is proportional to the area of the chip. So the more area we use, the more power we consume. So if we put 2 cores instead of doubling the frequency, we just use 2 times the power. Or if we build a smaller chip, we just use the same power. If you drive up the frequency, we'll use 2 times the power. So frequency won't go up. So single thread performance will kind of stagnate a little bit. It will grow like by 10% or so, but very, very little. The most of the floating point performance will come out of the SIMD vectorization, because all the cores won't grow per generation 2x. Still, we claim that we can double the floating point performance, and this is essentially, reflected by something we call Moore's law, that we have to double the floating point performance every 18 months. And this is where it comes from. It's the vectorization that makes that. And lastly, branch prediction. Take care that if you have conditional executions in inner loops, it will always fail, as long as they don't, as they're not always giving the same result. Right. So I have had some more slides about the memory subsystem, but we're already at the end of the hour. I would suggest we save them for now, and maybe come back to that later if you have the time. Sir?
So this might be a stupid question.
Probably not.
Don't have much of a background in hardware, but our applications work on unstructured grids, which essentially means you first have to access an index for an element,
Right.
and then access the field member which corresponds to that index.
Yeah.
Is that something which is going to break the pipeline, or is that something?
This is something that which will cause extensive, well, we call that a pointer chase, essentially, right? This is indirect indexing is difficult because we try to. There's another feature in the CPU that is called a prefetcher, that always tries to pick up the next element you might want to access. It will even try to adapt to your strides. So if you use different strides, it will see, it accesses an 8th. I'll pick the 8th, the 8th, the 8th, the 8th, and get it to you before you actually need it. But if you have indirect indexing, it won't be able to figure that out. So what you will see or directly experience is the latency of the memory instruction. Because you will look up one field, look up another field, and then load that. And it is very, very difficult for the CPU to deal with that. So you see directly the memory latency.
Right, and that is exactly what we see. So basically,
Yeah.
it's not going to be an issue for the pipeline because the pipeline has enough
No.
capacity.
Yeah.
It's going to be an issue for the prefetching the cache, essentially.
The cache and the memory.
Cache and memory.
You could, for example, like the outstanding reads and writes could overflow.
And potentially vectorization. Right?
Well, vectorization is probably not possible with this kind of thing. I mean, you have gather scatter.
Yeah.
If I remember back the old days where we had vector processors, it would work, right? But nowadays, we don't have a true vector architecture. This is not a vector machine. This is a SIMD machine, which is much less than a vector machine. But a vector processor costs nowadays around $300,000, I think, or something like that. So you wouldn't want to pay it. So it is, yes, so with indirect indexing, unstructured grids, linked lists, these are all difficult to treat. But they might be even more efficient than everything in order and do dense or so. So I think it's probably the best way to do it. It might be faster than anything else, but you have to live with the memory latency. You're probably scaling like stream benchmark or so.
Exactly what we see.
Yes. Very nice. We have good examples for that, like OpenFOAM is one of the guys that, the common workloads that have this behavior.
This superscalar pipeline, is it just some kind of vectorization?
Oh,
Or?
superscalar, no. Let's consider back. Where's the one that? It's slow. Okay. These guys here do vectorization. There's AVX floating point multiplication. There's AVX floating point addition. These guys treat vectors, SIMD vectors, not real vectors. This is superscalarity. Right? So look at that. You have a dispatcher, and you have different execution units and different memory accesses. Right? You can do them. You can use them all at the same time as long as you don't have dependencies between them. Now look at that. That's the same thing. It's just I probably should. It doesn't work that way, but right. So the scheduler will just you say, oh, add me this field to that field, and they say, no problem. I pass it to this one. Oh, where's the add? Here. I pass it to that, and you will have the next instruction multiply this field by that field in a vectorized manner. He'll pass it to this, right? But then you can additionally, at the same time, execute a load and store. This is exactly, in these two ports is where his application spends his time. Because it would say, I need this field, I need this field, and occasionally it will say, oh, now I got a value, I have to pass it on to this one. But unfortunately, it's not vectorized because they are not kind of contiguous pieces of memory. So it will occasionally end up here in the ALU doing a multiplication or an addition. But the rest will just be loads and stores. Yeah?
From that diagram, you can do an AVX addition at the same time as an AVX multiplication as long as they're independent.
Yes.
But
Yeah.
you can't do two AVX additions.
No. No, not yet. We can. No, we can't. We can't. Not yet. Yeah. But you can see. I mean, from the development of this platform, you can see this is certainly an option where the whole architecture can evolve. Right? We symmetrize that part, the loads and stores and the addresses. Now we can symmetrize that part, so we can do additional multiplication in the same two superscalar ports. And this will again, or consider it, we can do multiplication addition at the same time. So we can symmetrize two FMAs, essentially. And that will be one of the next steps, right? Why not? This is where the design is going. We need to double the floating point performance in the next version, because that's what the law says. So we have certainly no choice to do something else. It's pretty straightforward. But then, on the other hand, if you have to push all this floating point data in the pipeline, where does it come from? So there's a lot of this, a lot of thought just flows into how do we do that? Yeah, that's pretty tricky. I mean, there's a lot of efficiency also in the memory control. Everything can be done more efficiently, and we have higher levels of DDR3, for example. So we can do something there, but it is difficult to push all this data into the chip.
How much is a level 2 cache?
The level 2 cache is 256 kilobytes.
20?
256. And the level 1 is 32. 32 instruction and data. The instruction you usually don't care so much about. There's very special cases where the instruction cache really is an interesting part. Usually the level 1 data cache is the interesting part. Okay, sir, Nathan.
About hyper-threading.
What?
You're going to talk about hyper-threading?
Not really. Why? It's available. Okay. I never consider that a really important topic because usually the high-performance people say switch it off. It is not always true because we have cases where memory accesses or memory latency can be hidden in hyper-threading. Hyper-threading is, so for people who don't know, hyper-threading is a technology where we have an additional logical core to each physical core. So we have a number of, so this is a core, and we might have, or we might tell this operating system, hey, there's another one, which is actually not there. But we might have some resources of this core, like registers, fill buffers available. We don't have the execution unit because it costs us only, say, 1% of the chip area to make a logical core. But what this logical core can do, it can basically overcome, once this core stalls, it can take over the operation and with its own resources, take all the ALU with it and say, now I'm executing while you are busy. Kind of a thread switch in the processor. And this sometimes, for well, one workload where it really works good is a web server. The traditional example, right? So if you have people that run web servers, they usually switch on hyperthreading and have rather more cores because they can hide the memory latency in the hyperthreading, which is the only problem they really have because they need to read pages and cache all that stuff. The HPC people usually don't use that much because it would also share the computational resources, which they want to have exclusively for themselves. Do we have something about hyperthreading? Not a lot, right? Okay, I'll check it out. Maybe I find some material so we can speak about it. It's nothing I really, well, actually, will never ask about it.
The only thing about hyperthreading that I'm going to say tomorrow is turn it off into performance analysis.
Very good point. So it says turn it off is the dominant point. I mean, there are good workloads for hyperthreading, but on the other hand, the HPC people usually don't like it. If you look into the mic architecture, it's for hyperthreads. And you need it to hide this damn memory latency to get the data in. So it's right. So Mike, take it away.
All right. So first thing to understand is that we understand the core structure of Sandy Bridge. And the core structure, here's a couple of legal disclaimers, probably saying that nothing we say here is true or might change on short notice, something like that. And even that we might optimize kind of workloads for our own architecture. This is what we are essentially interested in. And this is a pretty complicated high-level diagram of the Sandy Bridge core. It is, well, any of these blocks in here have a quite complicated functionality usually. And between the blocks, there's even more units, which we don't show here. Buffers, fill buffers, load buffers, you never know, which might become important at one point. But this is essential parts that we think are most crucial for performance optimization. This is mostly too complicated. I assume that most people here are not from processor design, and they don't care so much about this kind of diagrams, and maybe ideally we would use a compiler, switch to 03, and just get good performance. It doesn't work that way usually, right? So we have to understand a little bit about that, but this is too complicated. We need to associate a couple of parts of this with particular functionality that comes from general considerations of computer architecture and design. There's a couple of technologies that Sandy Bridge implements, or mostly all processors nowadays do that. One of the most prominent one is certainly pipelining, and we will see that this is one of the features that brings us most performance, but it's also, it has the property that it's also disturbed the easiest. So a pipeline can be disturbed pretty quickly by some things you do in the code, just by doing something wrong. By the way, of course, you will get all the slides, so you don't have to write this stuff up. Right? So another technique that very much adds to the performance is branch predictions, something called out-of-order execution, which already gets a little bit esoteric, superscalarity, and SIMD execution. All of these techniques interplay a little bit with one another and actually add to performance, but can also handicap performance in some way. And we need to understand how and why. Usually, the first general steps every processor does is it fetches a new instruction. This is what it starts up with. I mean, if it comes up, it will bootstrap and just get a new instruction, load the operating system probably, right? And the first thing after that it will do is decode this instruction. It will find out what it wants to do with it. Is it an arithmetic instruction? Is it a memory operation? Is it something else, right? And if it has found out about that, it will try to execute this instruction. If it is something that is more arithmetic, like an addition, it will divert it to the so-called ALU, the arithmetic logic unit, and we'll see we have a couple of those in our processor. Or if it is something more organizational, probably a memory access, it will divert it to the unit that performs a memory address and loads this into the local registers. and if it number of instructions, the total time of the execution. And in the case of pipelining, we can ideally, over a longer workload, we can divide this by the number of stages. So we get immediately factors out of this performance tuning in the chip. Now this seems to be pretty good, and people like this idea. They actually pretty early in the development came up with this idea and executed it successfully. And greatly nowadays adds to the performance of our processes, of course. We'll see in the following that there is a couple of facts that interact in the pipeline that handicap this performance. And we need to take care of this, that this doesn't happen, because everything or all the performance depends on in current process is keeping the pipeline busy. If you stall the pipeline, where the performance comes down pretty quickly. So all analysis and optimization methods hereafter are basically set up to keep the pipeline flowing. So what can stall the pipeline? So we had all these couple of steps, like we fetch an instruction, we decode it, we execute it, we have memory access, for example, or we write it back. So, for example, if we want to fetch an instruction, we need to know which instruction we want to fetch. Consider a situation where we have an if condition and say, if a given variable is greater than 1, we want to go this path, otherwise we go the other path. So in this case, we don't know what the next instruction is because it depends on the outcome of the comparison. So we probably cannot even fetch this instruction because we don't know what the next instruction is. We may not be able to decode the instruction because there was no instruction fetched. Right. We may not be able to execute the instruction because the data that the instruction acts on. So for example, usually instructions come in kind of a function form, saying function name and then a function argument, maybe several arguments. Because some of the arguments might not be available because they depend on an earlier step of the calculation. So we have to wait for the actual execution of the previous instructions. We might have a memory access that cannot fetch any data because there is no data available, for example, in cache. There is no data available in the second level cache. I might have to go to the main memory to get the data. I might have to go to the disk to get the data. So we might have to wait before something happens. Right? Or I can't load the data into the register that was given to me, into the very local memory, because this register might still be in use. So all these kind of things can happen, and many more can happen. I mean, there's an infinite amount of problems in the pipeline can happen. And all this limits the pipeline execution. And this is to be avoided. The first thing we want to consider to improve the situation is actually predicting branches. Because when we look back at the previous slide, we had the issue that we want to fetch an instruction, but there is essentially, we don't know what instruction we want to fetch, because might be a condition that actually tells us which the next instruction is. So the way out of that is the branch prediction. So we try to actually speculatively have some results from these operations. It will write back the results into something called a register. And a register is just like something like a local storage. We have pretty few of those visible to the user. Internally, we have a lot. And we will just see what the registers probably means. OK. So we just saw there is fetch instructions, decode, execution, memory access, and write back of the results into memory. And usually people view that as one thing. We can execute that in a single step. Right? We will just execute a single step and wait until it's finished and then fetch a new instruction. What is a little bit more enlightening in this case is if we split it up into different execution units. And then, so these execution units are called stages of the pipeline. And then consider the outcome result. But if you now look at that, we can actually peruse the individual stages while, for example, the first instruction was fetched. We can already, and the first instruction is decoded, we can already fetch the next instruction. while the first instruction is executed and the second instruction is decoded, we can already fetch the third instruction, and so on and so on. So the first thing that actually adds to the performance, and people came up first with it very early in the development of computers, was to actually split up the execution into pipelining. Usually what brings that in terms of performance? What the original performance was the number of the time it takes to execute an instruction as a total thing, and the times the